Okay, I'm going to do 5.3 and 5.4 together because they go together. They're based upon pH calculations, so it just makes sense for me to introduce all of the equations that you will be using at once. And you don't have to memorize the equations. I give all of them to you, okay? All right, so we're going to first talk about the ionization of water. So when you've got a water molecule next to another, what can happen is one water molecule can donate a hydrogen to the other. So when something like that happens, it's called auto-ionization. And it's going to form a hydronium ion and a hydroxide ion. So guess what we can do? We can write an equilibrium expression for it because an equilibrium will form, okay? So this is the last type of equilibrium that we are going to encounter. Since these are both liquids, these would be excluded from your expression. So this would be the hydronium times the hydroxide ion concentration. And then instead of calling it KEQ, we will call it the water ionization constant, KW, which is also known as the ion product constant for water, okay? Now, this has a value depending upon the temperature that you're at. So if you're at room temperature, which is about 25 degrees Celsius, that means Kw equals 1 times 10 to the negative 14th, and that equals the hydronium times the hydroxide ion concentration. So I will be giving you this equation. You will never have to memorize it, okay? Let's turn to the next page. Obviously, if the hydronium and hydroxide ion concentrations are equal, you could substitute an X in for each one of those concentrations into the equation, which means you would end up with X squared is equal to 1 times 10 to the negative 14th, and you would take the square root of both sides to get 1 times 10 to the negative 7th, which would then be your hydroxide and your hydronium ion concentrations, okay? Let's take a look at the very bottom of the page. If you add acid or base to water, you're obviously going to change the hydronium and hydroxide ion concentrations. So if you increase the hydronium ion concentration, it will actually cause the hydroxide concentration to decrease, and vice versa. So what this means is hydronium and hydroxide are inversely related. Now, if you have an acidic solution, you'll have more hydronium than hydroxide. If they're neutral, they'll be equal. If it's a basic solution, hydroxide will be greater than hydronium. Let's turn to the next page. Let's take a look at a practice problem. So in number 1, it says they want us to calculate the hydronium and hydroxide ion concentration of 0.15 molar per chloric acid, and then they want us to justify that the solution is acidic. That means they want you to compare the hydronium to the hydroxide ion concentration. Now, HClO4 is an acid. That means it will break down into hydrogen ions and perchlorate ions. So if this concentration is 0.15 molar, that means the hydrogen ion concentration is 0.15 molar, and hydronium equals hydrogen. So that means it is 0.15, and we just need to calculate the hydroxide ion concentration. We'll do that using the 1.00 times 10 to the negative 14th equals hydronium times hydroxide. So you will put this value here, and then you'll divide both sides by 0.15. So this cancels, and you're going to end up with 6.7 times 10 to the negative 14. So now that we've solved for that, we need to justify that this solution is acidic. Well, the concentration of hydronium is significantly larger than the concentration of hydroxide. So what you would say is hydronium is greater than hydroxide. You could also compare their values, and that will justify that it's acidic. Okay? My only concern is when you're given a problem, and let's say you're given a substance that has a subscript on a hydroxide or a hydrogen, be super careful when you go to calculate the hydroxide or hydronium ion concentrations because you may mess that up. So for instance, in number 2, I'm not going to do this problem all the way through, but I want you to see that even though they're asking for the same thing as number 1, they told us that we have magnesium hydroxide, right? Magnesium hydroxide is MgOH2. So that means that you will end up having 2 hydroxides formed. So whatever the concentration is of that solution, you have to multiply the hydroxide concentration by 2 to get the real hydroxide ion concentration that's in the solution. Does this make sense? Okay. Now you can build, like, this problem doesn't give you a concentration. You can build upon what we did in a previous section where you have the KSP. And from the KSP, you can calculate the hydroxide ion concentration. What I mean by that is KSP for magnesium hydroxide in the table is 5.6 times 10 to the negative 12. So this equals the magnesium ion concentration times the hydroxide squared. If you put an x in here, this would have to be a 2x, right? So this would become x. This would be 2x squared, and then you would solve for x, calculate hydroxide and hydronium from there, okay? Okay, now, the last part, is there anything else, or did I take it out? We're done? That's all. That's all. Okay, so that's this section. Let's turn to the next section.